A rock the size of a house is racing toward Earth, and 1 week ago, no one on the planet knew it existed. Astronomers spot it as a faint speck in the Arizona night sky. 2 days later, it has a name, 2026 JH2. 6 days after that, it is 35 meters wide, moving 20,000 miles an hour, and closing in fast. We are about to follow this rock past the moon, past our satellites, and within 56,000 miles of our planet's surface. That is closer than some of the machines orbiting Earth right now. A blue whale could fit inside it, end to end, and astronomers are racing the clock to learn everything they can before it disappears again for almost 4 years. If you enjoy chasing mysteries like this one, hit like and subscribe. It helps this channel keep digging up the strangest corners of our universe. A house-sized visitor is closing in, and it showed up almost without warning. Prepare yourselves, we begin. On the night of May 10th, a telescope on a mountain in Arizona takes a picture of empty space. Nothing looks unusual, just stars, black sky, and one faint dot that should not be there. That dot moves. Stars do not move. Rocks do. A computer flags it. A human checks it. Neither one knows yet what they are looking at. It could be a scrap of space junk. It could be a comet. It could be nothing at all. A smudge on the lens. A trick of the light. The team keeps watching. By morning, the dot is still there, and it has shifted position again. Something small, something fast, and something completely unknown is drifting through the dark, somewhere between Earth and the outer planets. Nobody on the entire planet has ever seen this object before tonight. This is how almost every asteroid story begins. Not with a warning, not with an alarm, with one tired astronomer squinting at a screen, wondering if a single pixel might be real. The mountain this dot was found on is called Mount Lemmon, just outside Tucson. Every clear night, a 60-inch telescope up there sweeps the sky, searching for exactly this kind of thing. Small, dark, and dangerous rocks that could sneak up on Earth without warning. Most nights, it finds nothing worth chasing. Tonight is different. The astronomers give the object a temporary name, a string of letters and numbers that means nothing to anyone outside the observatory. For now, it is just a mystery, a math problem, a handful of dots on a screen that need 3 things before anyone can say anything useful. More pictures, more nights, and more telescopes, pointed at the same tiny patch of sky. Here is the part that should make your skin prickle a little. Nobody found this rock a month early. Nobody found it a year early. It appeared out of the darkness less than 8 days before it would come closer to Earth than almost anything ever tracked before it. Think about that gap for a second. 8 days is barely enough time to plan a birthday party, let alone measure an object racing through space at 20,000 miles an hour. And yet that is exactly the window scientists were given. One faint dot, one short window, and one question nobody could answer yet. How close is this thing actually going to get? Astronomers have a name for objects like this. They call them near-Earth objects, a plain phrase for rocks whose paths bring them uncomfortably close to our planet. Most are harmless. Most stay far enough away that nobody outside a research lab ever hears about them. This one would not stay quiet for long. Within 48 hours, that faint dot on a screen in Arizona would have an official name, an official orbit, and an official spot on every asteroid tracker on Earth. The clock had already started, and almost nobody watching the night sky that week had any idea it was running. Somewhere above Tucson, Arizona, a telescope works the night shift every single night, scanning the sky for things that should not be there. This is the Mount Lemmon survey, and its entire job is finding dangerous rocks before they find us. Picture a camera so sensitive it can catch a boulder reflecting sunlight from millions of miles away, a rock smaller than a school bus, glowing about as bright as a candle held up on the far side of a football field. That is the kind of needle this observatory hunts for in a haystack the size of the solar system. The telescope does not work alone. It takes picture after picture of the same patch of sky, then compares them. Stars stay still. Planets barely move. Anything that shifts position between photos gets flagged instantly by computer software built for exactly this purpose. A human then checks every flag because computers miss things, and humans catch what computers cannot. This is not a hobby project. It is part of a global safety net, one built after scientists realized something uncomfortable. Earth gets hit by space rocks more often than most people think, and for decades, nobody was seriously looking for the next one. Small impacts happen more than you would guess. Every single day, tons of space dust burns up harmlessly in our atmosphere. But every few decades, something bigger slips through, something the size of a car or a house or worse. The Mount Lemmon survey exists to catch the bigger ones early, while there is still time to do something about it. Here is where the story gets uncomfortable. Even the best telescope on Earth cannot see everything. Small asteroids are dark, often as dark as fresh asphalt, and they only reflect a whisper of sunlight. An object under 30 meters wide, roughly the length of 3 school buses parked end to end, might stay completely invisible until it is only days away from arriving. That is not a flaw in the system. That is physics working against us. Distance and darkness hide these rocks until the very last moment, no matter how good our telescopes get. So when the Mount Lemmon survey caught that faint dot on May 10th, the team did not know if they were looking at a harmless flyby or the beginning of a genuine emergency. All they had was a moving point of light and a responsibility to figure out as fast as possible exactly what it was. Within hours, they alerted other observatories around the world. Confirmation requests went out. More telescopes turned toward the same coordinates, hunting for the same faint dot, racing to answer one question before the object slipped past Earth for good. What they would find over the next 2 days would turn a quiet Arizona night into one of the tightest, most closely watched asteroid stories of the year. A blurry dot on a screen means nothing by itself. Space is full of blurry dots. What turns a smudge of light into a confirmed, tracked, named asteroid is a process that moves fast. And it started the moment Mount Lemmon's data reached other observatories. Within hours, telescopes in different states, and eventually different countries, pointed at the same coordinates in the sky. Stewart Observatory checked it. Farpoint Observatory in Kansas checked it. Magdalena Ridge Observatory in New Mexico checked it. Each one took its own photographs, at its own angle, from its own location on Earth. Why does that matter so much? Because a single telescope only gives you one line of sight, one guess at direction. Multiple telescopes, spread across hundreds of miles, let scientists triangulate. Imagine 3 friends spotting the same bird from 3 different windows in the same house. Compare all 3 views, and suddenly you know exactly where that bird is flying and how fast. That is what happened here. Except instead of a bird, it was a rock racing through space at 20,000 miles an hour. Every new photograph fed into a shared system, one used by astronomers worldwide, run by an organization called the Minor Planet Center. Their entire purpose is collecting sightings like this one, checking them against everything already known, and confirming when something new and real has been found. 2 days after that first faint dot appeared on a screen in Arizona, the Minor Planet Center made it official. The object was real. Its orbit was confirmed, and it received a permanent name, 2026 JH2. That name is not random. The letters and numbers follow a coding system astronomers use worldwide, marking the year of discovery and the order it was found within that stretch of days. It is less a name and more a birth certificate, proof that this rock is now catalogued, tracked, and impossible to lose again. Here is what should stop you for a second. 2 days. That is how long it took to go from an unknown blur to a fully confirmed, internationally tracked object, one now expected to pass closer to Earth than almost any asteroid its size ever recorded. Compare that to how long some questions in science take. Curing a disease can take decades. Understanding a black hole can take a century. But confirming a new asteroid, one racing toward a record-setting close pass, took less time than it takes most people to plan a weekend trip. That speed is not luck. It is the direct result of a global network built specifically for moments like this. Telescopes and scientists ready to move the instant something unexpected appears. And 2026 JH2 had just become the most unexpected thing in the sky. You would think, with all our telescopes and cameras, that scientists could just look at an asteroid and measure it, the same way you would measure a rock in your backyard. They cannot, not even close. Here is the problem. 2026 JH2 never appeared as a shape in any photograph. It appeared as a single point of light, a dot with no visible edges, no visible surface, nothing you could hold a ruler up to. From Earth, this rock was always too small and too far away to resolve into anything but a pinprick of brightness. So how do scientists estimate size from a dot? They measure how bright that dot is, then work backward. Picture two flashlights in a dark field at night. One is small and shiny, held close. The other is large and dull, held farther away. Both could look exactly the same brightness from where you are standing. Size and reflectivity blend together into a single number of light, reaching your eyes, and untangling them requires guesswork. Asteroids work the same way. A shiny, reflective rock could look bright while actually being small. A dark, dull rock could look just as bright while actually being much larger. Without knowing exactly how reflective the surface is, scientists are stuck with a range, not a single number. For 2026 JH2, that range stretched from about 15 meters to 35 meters wide. In plain terms, that is somewhere between 50 feet and 115 feet, roughly a spread from a large house to something approaching 1/3 the length of a football field. That is a massive amount of uncertainty for something racing toward a record close pass by our planet. This is not a failure of science. It is an honest admission of what is actually knowable given the tools we have. Astronomers call the brightness measurement absolute magnitude, and for this asteroid, that number sat at 26.3, a figure precise down to the decimal, wrapped around a size estimate that still spanned tens of feet in either direction. Only two things could narrow that range further. Radar, if a large enough dish happened to be pointed the right way at the right time, could bounce a signal directly off the rock and measure its shape with real precision. Or a spacecraft, flying close enough to snap an actual photograph. Neither option existed for this flyby. There was no time and no mission in place. So scientists did what they always do in this situation. They gave their best range, admitted the uncertainty out loud, and kept refining the number as more data arrived. One thing was not in question, though. Whatever its exact size, this rock was big enough and close enough that getting the number right actually mattered. Numbers alone do not mean much. 50 feet, 115 feet. Those words slide right past your brain unless you can picture them standing in front of you. So let us build that picture. Take an average 2-story house, roofline included. That is close to the smaller end of this asteroid's size range. Now stretch that house out until it is over twice as long. That gets you closer to the larger end of the estimate, something brushing up against the length of the biggest animal that has ever lived on Earth, the blue whale. A blue whale can stretch past 100 feet nose to tail, heavier than a line of loaded school buses. 2026 JH2, at its largest possible estimate, matched that length almost exactly. Not in weight, not in shape, just in raw, straight line size, tumbling silently through space instead of swimming through an ocean. Here is another way to picture it. A football field runs 100 yards, or 300 feet, end zone to end zone. At its biggest estimated size, this asteroid stretched close to 1/3 of that entire field. Imagine a rock the length of the distance from the goal line to somewhere near the 35-yard line. moving through space at 20,000 miles an hour. That speed deserves its own picture too. Commercial jets cruise around 550 miles an hour. This asteroid moved almost 40 times faster than that, fast enough to cross the entire continental United States in under 8 minutes, if it were somehow skimming along the ground instead of racing silently through space. Now here is where the comparison turns serious. Objects in roughly this size range are not just theoretical concerns. One nearly identical in scale already made history, exploding without warning over a Russian city in 2013. That event, and what it revealed about rocks this size, deserves its own chapter later in this story, because it changes everything about how seriously scientists take an object like this one. For now, hold on to the picture. A rock somewhere between a house and a blue whale, moving faster than almost anything human-made, discovered only days before making one of the closest recorded passes by an object its size. Numbers like 15 to 35 meters can blur together and disappear from memory within seconds. A blue whale racing past your planet at 20,000 miles an hour does not disappear so easily, and this is the part that should sit with you. Every single detail scientists were working with, the size, the shape, the exact path, all of it was still shifting, still uncertain, right up until the very final hours before the flyby. The size of the mystery had not changed. The time left to solve it kept shrinking by the minute. 7 days. That is the entire window scientists had, start to finish, between spotting this asteroid for the first time and watching it reach its closest point to Earth. 7 days to answer questions that, for larger and more famous asteroids, take years to fully resolve. Compare that to Apophis, another well-known asteroid, first discovered back in 2004. Scientists have spent over 2 decades tracking its orbit, refining its path down to precise detail, preparing for a close approach, still years away. That is the normal timeline for asteroid science. Careful, patient, unhurried. 2026 JH2 offered none of that luxury. Every calculation had to happen fast, because the rock itself was moving fast, and the window to gather more information was closing by the hour. Here is why speed matters so much in orbital math. To calculate exactly where an asteroid is headed and how close it will actually pass by Earth, scientists need multiple observations spread across time. 2 points barely sketch a rough line. 10 points, spread across several days, sharpen that line into something close to certain. With only 7 days total, and the first day or two spent simply confirming the object was real, scientists were left with a painfully short stretch to nail down the details. Every extra night of clear skies, every extra telescope willing to point at the same patch of darkness, added crucial data. Every cloudy night, every missed observation, meant more uncertainty carried forward. This is why astronomers around the world dropped other projects the moment word spread. Telescopes that had been scheduled to study distant galaxies redirected toward one small, fast-moving rock instead. Coordinated effort, shared data, constant updates, all of it aimed at one goal: nail down the path before the object arrived. Picture trying to predict exactly where a thrown ball will land, but you only get to watch it for the first half second after it leaves someone's hand. That is roughly the challenge scientists faced here, except the ball was a house-sized rock, and the stakes involved millions of people below its path. By the 5th day, the picture had sharpened considerably. Scientists could say with real confidence that this asteroid posed no danger of impact. What remained uncertain, right up until nearly the final hours, was the exact distance of the close approach itself, down to the mile. Every additional data point tightened that number. Every hour that passed brought scientists closer to certainty, and the entire world of professional asteroid tracking spent that week doing something it rarely gets forced to do, working against an unforgiving, fast-ticking clock. The stopwatch was already running when the story began. Nobody chose to start it. The asteroid did. To understand where 2026 JH2 came from and where it was headed next, you need to understand its orbit. That word sounds complicated. It is not. Picture a kid on a playground swing, pumping their legs to go higher and higher. At the bottom of the swing, they are moving fast, feet skimming close to the ground. At the very top, on each side, they slow down almost to a stop before gravity pulls them back. That rhythm, fast at the bottom, slow at the top, is exactly how this asteroid moves through space. Except instead of swinging back and forth on a rope, it swings around the sun on an oval-shaped path. Scientists call this an elliptical orbit, and this asteroid's version was especially stretched out, especially lopsided. At its closest point to the sun, called perihelion, it swings in almost exactly as close as Earth itself. That is, the bottom of the swing, the fast part, the part where speed builds up. At its farthest point from the sun, called aphelion, this rock drifts out nearly as far as Jupiter, one of the largest planets in our solar system. That is the top of the swing, the slow part, the part where the rock barely seems to move at all. Here is the piece that should surprise you. This asteroid does not orbit the sun in a smooth, gentle circle, like a spinning top. It stretches out toward Jupiter, then swings all the way back in toward Earth's neighborhood, again and again, on a repeating loop that takes roughly 3 3/4 years to complete. Every time it swings back through the inner solar system, near the bottom of that long oval path, there is a chance, however small, that its timing lines up with Earth's own position. Most of the time, the two paths miss each other by enormous distances. This particular pass, in May of 2026, they came remarkably close. Think of two kids on separate playground swings, set at slightly different angles, occasionally swinging through the exact same patch of space at the exact same moment. Most swings, they miss each other completely. Every so often, the timing lines up almost perfectly. That is the mechanical, almost mathematical explanation behind an asteroid flyby. Not chaos, not random danger dropping from the sky without warning. Two predictable paths, shaped by gravity, occasionally crossing close together. Understanding this orbit did more than satisfy curiosity. It told scientists something even more important. This was not a one-time visitor passing through and vanishing forever. This rock would be back, and that detail changes the entire shape of the story from here. Here is a detail that separates this asteroid from countless others. 2026 JH. 2 is not a stranger passing through once and disappearing into the darkness forever. It is a repeat visitor, locked into a loop that brings it back near Earth's neighborhood roughly every 3 3/4 years. That number comes from something called an orbital period, the exact amount of time it takes an object to complete one full lap around the Sunday Earth's orbital period is 1 year by definition. This asteroid's stretched, oval-shaped path takes almost 4 times as long to complete a single circuit. Picture 2 racetracks side by side, one small and tight, representing Earth's nearly circular path. The other track is long, narrow, and stretched almost to the point of breaking, reaching all the way out toward Jupiter before curving back. 2 racers start at the same line. The one on the small track finishes lap after lap, while the one on the long track is still making its way around just once. Every time that second racer, our asteroid, completes its long stretched lap and swings back through the inner solar system, it crosses paths with Earth's own racetrack. Sometimes, Earth is nowhere near that crossing point when the asteroid arrives. Sometimes, like this May, the timing lines up far more closely. This detail matters enormously for scientists tracking this rock. A one-time visitor, seen once and never again, offers a single data point and nothing more. A repeat visitor offers something far more valuable, a chance to refine the orbit further with each future pass, and a chance to prepare, calmly and without rush, for whatever comes next. Here is where curiosity should spike. If this rock returns roughly every 3 3/4 years, when does it come back? Scientists can already calculate a rough answer, though the exact distance of any future approach depends on tiny details in the orbit that only sharpen with more observation time. Unlike this most recent encounter, born from a mere 7 days of frantic, last-minute tracking, future passes will not sneak up the same way. This object is catalogued now, tracked, understood, at least in broad strokes. The next time it swings back through Earth's neighborhood, scientists will already know it is coming, likely years ahead of time instead of days. That single fact quietly reshapes the entire emotional tone of the story. This was not humanity dodging one lucky, unexpected bullet. It was humanity spotting a fast-moving object at the very last possible moment and getting away with it. The next visit will not require luck. It will require patience and the kind of careful, unhurried tracking scientists wish they had been given this time around. Follow this asteroid's orbit outward, past Earth, past Mars, past the scattered rubble of the asteroid belt, and you eventually arrive near the orbit of Jupiter itself, the largest planet in our solar system. That is how far this rock travels on the outer edge of its long, stretched path. Jupiter sits roughly 5 times farther from the Sun than Earth does. To put that in a more familiar scale, if Earth's distance from the Sun equaled the length of a single football field, Jupiter would sit 5 full football fields away. This asteroid's farthest point, called aphelion, stretches almost that entire distance before gravity finally pulls it back. Why does that matter for a story about a close pass by Earth? Because it reveals just how wildly this object's environment changes across a single orbit. Near Earth, sunlight is strong, temperatures swing wide, and the asteroid moves fast, whipped along by the Sun's gravity at close range. Out near Jupiter's distance, sunlight fades to a fraction of its strength near Earth, and the asteroid slows to a crawl, drifting almost lazily through the emptier, colder outer solar system. This is what scientists mean when they call an orbit highly elliptical. Not a gentle variation, but an extreme one, swinging between 2 dramatically different environments on a single repeating loop. Jupiter itself plays a quiet but important role in this story, even without any direct involvement in this particular flyby. Jupiter's gravity is famously powerful, strong enough to bend and reshape the orbits of countless smaller objects that wander too close to it. Some asteroids get flung inward toward the Sunday, others get hurled outward into deep space entirely. A small but real number end up trapped in orbits that repeatedly cross paths with Earth, exactly like this one. Some scientists suspect that objects like 2026 JH2 may have originally started out somewhere in the asteroid belt between Mars and Jupiter, only to have their paths gradually reshaped over millions of years by exactly this kind of gravitational nudging, until eventually their orbit crossed into Earth's neighborhood entirely. That means this rock's origin story likely stretches back millions of years, shaped slowly by forces far larger than itself, long before any human ever discovered it. It could have been drifting on some version of this exact path since long before telescopes, since long before Arizona had an observatory, since long before humans existed to notice it at all. And yet, for 1 week in May of 2026, all of that ancient, slow-motion history collapsed down into something urgent and immediate. A rock, shaped over millions of years by Jupiter's distant gravity, was about to make its closest recorded pass by our planet, and scientists had only days to prepare. Every asteroid gets sorted into a family based on the shape of its orbit, and 2026 JH2 belongs to one of the more attention-grabbing groups, the Apollo asteroids. Here is what earns an asteroid that label. Its orbit must stretch out beyond Earth's own distance from the Sun, while also, at some point, crossing directly through Earth's orbital path. Not near it, not close to it, directly through it. Picture 2 lanes on a highway that mostly run parallel to each other, side by side, safely separated. Now picture one of those lanes occasionally curving over and merging directly across the other before curving back again. That merge point is where danger, however small, briefly becomes possible. That crossing point does not mean a collision happens. It means one becomes mathematically possible, if timing ever lined up exactly wrong. Earth and an Apollo asteroid can cross the same point in space thousands of times, across thousands of years, and never once collide, simply because both objects need to arrive at that exact crossing point at the exact same moment for anything to happen. Named after the very first asteroid discovered with this orbital pattern back in the 1930s, Apollo asteroids have earned a reputation as some of the more closely watched objects in the sky, precisely because that crossing potential exists. Scientists do not panic over every Apollo asteroid. They track them. 2026 JH2 earned this classification just 2 days after its discovery, once its orbit had been confirmed enough to prove its path swept across Earth's own. That single classification told scientists something crucial before any size estimate, before any distance calculation. This rock's orbit deserved serious, careful attention. Thousands of Apollo asteroids are currently known and tracked. The overwhelming majority pose no threat whatsoever, their crossing points falling nowhere near Earth's own position at any point in the foreseeable future. A small handful earn closer monitoring, their paths requiring regular updates as more observations refine exactly where they will be, decades or even centuries down the line. This is the invisible, ongoing work most people never think about. An entire global system exists specifically to sort, classify, and monitor rocks like this one, quietly running in the background every single day, long before any particular asteroid becomes a headline. 2026 JH2 spent barely a week as an anonymous, uncatalogued rock in the darkness. The moment it earned the Apollo classification, it stepped into a much larger, much older story, one involving thousands of similar objects, decades of tracking effort, and a planetary defense system built specifically to answer one question over and over again. For every new rock discovered, does this one matter, and how closely do we need to watch it? Here is a detail worth slowing down on because it trips people up constantly. 2026 JH2 crosses Earth's orbit. That phrase sounds alarming. It is not the same thing as saying it crosses paths with Earth itself. Space is unimaginably vast, and orbits are not solid lines drawn in the sky. They are three-dimensional paths, stretched across enormous distances, tilted at different angles, and most importantly, occupied by their respective planets and asteroids only at specific moments in time. Picture two entire running tracks, not just two lanes, but two full ovals, one tilted slightly against the other, crossing at exactly 2 points. Runners on each track could pass through those crossing points thousands of times across a season and never once run into each other, simply because they rarely reach that exact spot at the exact same second. Earth takes 1 year to complete its lap. 2026 JH2 takes nearly 4 years to complete its own, much larger lap. For an actual collision to happen, both objects would need to arrive at precisely the same crossing point in the same tiny window of time, down to a matter of minutes. The odds of that happening by pure chance, on any given crossing, are extraordinarily small. That is exactly why an object can be classified as Earth crossing, tracked for years, monitored by professional astronomers, and still pose essentially zero real danger for the foreseeable future. This is also why scientists reacted to 2026 JH2 with genuine excitement rather than alarm, even while confirming its close pass. Crossing Earth's orbital path is a geometric fact about its route through space. Actually threatening Earth requires something far more specific and far rarer, both objects occupying that exact same point in space at that exact same moment. For this particular flyby, scientists confirmed early on, well before the closest approach, that no impact was possible. The remaining uncertainty was never about danger. It was about precision, nailing down exactly how close, in miles, this rock would pass by, and exactly when. That distinction matters enormously for how you should picture this entire story. This was never a countdown toward possible disaster. It was a countdown toward measurement, toward observation, toward answering a purely scientific question about exactly how close a rock this size would swing past Earth's surface, closer than almost anything ever recorded. Understanding that difference changes the entire emotional shape of what comes next. The excitement building around this asteroid was never really about fear. It was about opportunity. A rare, narrow window to study something up close that almost never comes this near. Every detail in this story eventually points toward one number: 56,000 miles. That is how close scientists calculated 2026 JH2 would come to Earth's surface at its nearest point. Numbers like that slide past the brain unless you can picture what actually fits inside that gap. So picture it. Commercial airplanes cruise at around 6 miles above the ground. Stack over 9,000 of those cruising altitudes directly on top of each other, and you would still be several thousand miles short of 56,000. Here is a more useful comparison. Geostationary satellites, the kind that beam television signals and weather data across the globe, orbit at around 22,000 miles above Earth's surface. This asteroid passed more than twice that distance beyond those satellites, but still remarkably close by cosmic standards. The International Space Station, by contrast, orbits far closer to home, only about 250 miles up. 56,000 miles is over 200 times that distance. This was never a case of an asteroid buzzing directly past astronauts in orbit. It stayed well beyond low Earth orbit, out past the ring of communication satellites, but still shockingly close compared to how far away most asteroids typically pass. That is the real headline hiding inside this number. Most near-Earth asteroids, even ones classified as potentially hazardous, tend to pass by at distances measured in millions of miles, not tens of thousands. 56,000 miles place this particular flyby in genuinely rare territory, one of the closest passes ever recorded for an object of this size. Scientists have a specific unit they use to measure distances like this: lunar distance, based on the average gap between Earth and the Moon, roughly 238,000 miles. By that measurement, this asteroid passed by at less than a quarter of the distance to the Moon itself. Picture the Moon hanging in the night sky, that familiar glowing circle everyone has looked up at their entire life. Now picture something the size of a house, tumbling silently through space, at barely a quarter of that same distance. That is how close 2026 JH2 actually came. None of this distance ever put Earth in genuine danger. The math confirmed that clearly, well before the flyby occurred. But the sheer closeness of the pass is exactly why this story captured global attention, why telescopes around the world turned toward the same patch of sky, and why scientists treated this particular week as a rare, valuable opportunity rather than a routine observation. 56,000 miles sounds abstract on its own. Measured against satellites, against the Moon, against everything orbiting above your head right now, it becomes something else entirely. Proof that space, even nearby space, still holds surprises capable of sneaking up with barely a week of warning. Let us build one complete picture, layer by layer, of everything sitting between Earth's surface and the point where 2026 JH2 passed by. Start at ground level, where you are standing right now. Climb upward, and within roughly 250 miles, you would reach the orbit of the International Space Station, the closest major human structure to Earth, home to astronauts living and working in space full-time. Keep climbing. Around 22,000 miles up, you would reach the ring of geostationary satellites, the machines responsible for beaming live television, weather forecasts, and global communication signals across the planet. These satellites move at exactly the same speed Earth rotates, which lets them hover above the same spot on the ground constantly, day and night. Keep climbing past that ring, and the space between satellites and the Moon grows genuinely vast, filled mostly with nothing at all. Somewhere in that gap, at around 56,000 miles up, more than twice the distance of those geostationary satellites. 2026 JH2 passed silently through, moving nearly 20,000 miles an hour. Keep climbing even farther, and only after covering more than 4 times that remaining distance would you finally reach the Moon itself, hanging at an average distance of 238,000 miles from Earth. Laid out this way, the picture becomes obvious. This asteroid threaded a narrow gap well beyond our satellites, but still less than a quarter of the way to the Moon. It occupied a strange middle zone, far closer than almost any asteroid typically gets, yet still comfortably beyond anything humans have built or sent into space. Here is a comparison that might land even harder. On a clear night, step outside and look up at the sky above your own house. Somewhere in that same vast darkness, invisible to your naked eye, satellites drift by, constantly, silent and unnoticed. This asteroid passed through that same general region of space, just much farther out, moving far faster, and completely undetected by anyone without a telescope. You never saw it. Nobody standing in their backyard that night saw it either, not without specialized equipment. It stayed 100 times too faint for human eyes to catch, even at its absolute brightest and closest point. And yet it was there, closer to Earth than the Moon has ever been in your entire lifetime. That contrast, something enormous and record close, yet completely invisible to the naked eye, sits at the heart of why this story fascinated scientists so deeply. Proof that Earth's neighborhood is far busier and far less empty than it feels standing quietly in your own backyard on an ordinary night. Here is a fact that confuses people almost every time an asteroid story like this one breaks. 2026 JH2 passed by at a distance more than twice as far as our satellites. Yet somehow, headlines still framed this as closer than a satellite. Both statements are true, and understanding why reveals something important about how orbital distances actually work. Most satellites orbit incredibly close to Earth, some just a few hundred miles up, others out around 22,000 miles for the geostationary ring. This asteroid, at 56,000 miles, technically passed beyond that entire ring of communication satellites. So why did so many headlines describe it as passing closer than satellites? Because a small number of specialized satellites, ones designed for very specific scientific or military purposes, orbit much farther out than the familiar geostationary ring, some reaching tens of thousands of miles beyond it. Compared to those farther-flung outliers, this asteroid's 56,000-mile pass genuinely counted as closer. This detail matters less for the exact comparison, and more for what it reveals about coverage. When a story sounds dramatic, different outlets sometimes chase the most striking comparison available, rather than the most typical one. Here, both framings are technically accurate. One simply sounds far more thrilling than the other. None of that changes the core scientific fact. Regardless of exactly which satellites sit closer or farther than this particular flyby, the actual distance, 56,000 miles, never came close to threatening a collision with Earth. Here is why distance alone should not trigger fear, even at numbers this close by cosmic standards. Space near Earth is enormous, far larger than intuition suggests. An asteroid passing 56,000 miles away is still passing through empty space, nowhere near Earth's actual surface, nowhere near the thin layer of atmosphere that protects everything living below it. Picture standing in the middle of an empty football stadium, completely alone. Now picture a single grain of sand landing somewhere in the parking lot outside. That grain of sand did not come close to hitting you, even though, relatively speaking, it landed in the same general neighborhood as the stadium itself. Scale that comparison up, and you start to understand just how much empty space still separated this asteroid from any actual danger. Scientists confirmed zero chance of impact days before the flyby occurred, using orbital calculations precise enough to rule out collision entirely, long before the exact distance in miles had even been finalized. The excitement surrounding this event was never really about survival. It was about rarity, about proximity, about how unusually close a rock this size managed to sneak without ever posing any genuine threat at all. That distinction, close but never dangerous, would matter even more as scientists prepared for the flyby's final, most intense hours. At NASA's Jet Propulsion Laboratory, tucked into the hills outside Los Angeles, a team of scientists spends every single day tracking objects exactly like 2026 JH2. This is the nerve center of American asteroid monitoring, home to a database containing the orbits of nearly every known object that ever wanders close to Earth. As the countdown toward closest approach ticked down through its final days, this laboratory became one of the most important places on the entire planet for anyone hoping to understand exactly what was about to happen. Here is what that work actually looks like. Stripped of any Hollywood drama, scientists gather every new observation streaming in from telescopes around the world, feed that data into orbital calculation software, and continuously refine their prediction of exactly where this asteroid will be, down to the mile, at any given moment. Each new data point sharpens the picture slightly. Early estimates carried real uncertainty, distances that could shift by hundreds or even thousands of miles in either direction. As more telescopes contributed more observations across those final days, that uncertainty steadily shrank, the predicted path tightening with each passing hour. Picture trying to draw a perfectly straight line freehand, blindfolded, using only occasional taps on your shoulder to guide your direction. The first few taps barely help. By the 20th tap, your line has become remarkably accurate. That is roughly what happened here, except the taps were telescope observations, and the line was an asteroid's path through space. By the time closest approach arrived, scientists at the laboratory had narrowed their prediction down to a genuinely precise figure, 91,572 kilometers, with an uncertainty of only about 186 kilometers in either direction. In miles, that meant scientists knew this asteroid's closest distance to within roughly 115 miles of certainty, an extraordinary level of precision for an object first spotted barely a week earlier. This laboratory does not exist solely for moments like this particular flyby. It maintains constant watch over thousands of known near-Earth objects, updating their orbits year after year, decade after decade, building the foundation that let scientists respond so quickly when this new rock first appeared. That existing infrastructure, quiet and unglamorous most days of the year, is precisely what allowed a 7-day window to actually work. Without decades of prior tracking experience, without an established global network of cooperating observatories, without software refined over years of practice, this story could have played out very differently. Instead, as the final hours counted down, scientists at the Jet Propulsion Laboratory watched their prediction sharpen into something close to certain. Somewhere out past the ring of satellites, a house-sized rock was closing in fast, and for the first time all week, everyone finally knew almost exactly where it was headed. Even with all that precision building around this asteroid's path, one detail stubbornly refused to sharpen: its exact size. Right up until the final hours before closest approach, scientists were still working with a range, not a single confirmed number. This might seem strange. How can scientists pin down an object's location to within 100 miles while its actual size remains uncertain by tens of feet in either direction? The answer comes down to what each measurement actually requires. Calculating an asteroid's path relies on tracking its position against the background stars, night after night, then applying gravity's well-understood mathematical rules to predict exactly where it travels next. Gravity behaves predictably. Once you have enough position data, the math locks into place with remarkable confidence. Size works completely differently. As explained earlier in this story, size depends entirely on brightness, and brightness depends on both size and reflectivity tangled together into a single number. Without a more direct measurement, like radar, that tangle simply cannot be fully undone. Here is the frustrating part for scientists working this case. Radar observations, the kind that could bounce a signal directly off the asteroid's surface and measure its true dimensions, require enormous dish antennas capable of transmitting and receiving extremely precise signals across tens of thousands of miles. Only a small handful of facilities on Earth can perform this kind of observation, and scheduling time on them, especially with only days of advance notice, proved impossible for this particular flyby. So the size range stood 15 to 35 meters, house-sized to blue whale-sized, unresolved through closest approach and beyond. Scientists made peace with that uncertainty because refusing to publish results until every detail was perfect would have meant saying nothing useful at all. At a moment when the public deserved real information, this uncertainty offers a valuable lesson about how science actually works, especially science conducted under serious time pressure. Confidence and precision are not the same thing. Scientists were extremely confident this asteroid posed zero danger of impact, a conclusion drawn from precise orbital math. They remained genuinely uncertain about its exact size, a completely separate question requiring different tools they simply did not have time to access. Real science regularly looks like this, confident about some things, honestly uncertain about others, and clear about exactly which is which. That honesty matters more than false precision ever could. As closest approach finally arrived, scientists were prepared to learn what they could, accept what remained unknown, and treat every new photograph as one more small piece of a puzzle that might never fully resolve. Somewhere between 50 and 115 feet wide, a genuine mystery was about to pass closer to Earth than almost anything else its size ever recorded, its exact dimensions still hidden behind a curtain that not even the world's best telescopes could fully pull back in time. Every story about a house-sized asteroid eventually arrives at the same comparison, because one event, more than any other, taught scientists exactly what a rock this size can actually do. That event happened over Russia in February of 2013, above a city called Chelyabinsk, an asteroid roughly 20 meters wide, close to the middle of 2026, JH2's own size range, entered Earth's atmosphere completely undetected. Nobody spotted it beforehand. No telescope flagged it. No warning reached anyone on the ground below. It simply appeared, streaking across the morning sky at incredible speed, brighter than the sun itself for a few brief seconds. The rock never reached the ground intact. Instead, roughly 14 miles above the city, it exploded in the atmosphere with tremendous force, a blast releasing energy equivalent to nearly 30 times the power of the atomic bomb dropped on Hiroshima. That shockwave raced outward and downward, reaching the ground moments later. Windows shattered across the city. Roofs collapsed under the pressure. Over 1,000 people were injured, most from flying glass as the shockwave blew out windows in homes, schools, and offices across the region. Remarkably, nobody died, though the damage stretched across an area covering multiple towns. This is why scientists take objects in this size range so seriously, even when, like 2026 JH2, they pose absolutely no danger of impact. Chelyabinsk proved, in the most dramatic way possible, that a rock this size carries enough energy to genuinely hurt people, shatter buildings, and terrify an entire region, all without ever touching the ground. Here is the detail that should genuinely unsettle you. Chelyabinsk arrived with zero warning. No telescope caught it beforehand, because it approached from the direction of the sun, invisible against the glare, completely undetectable, using the observation methods available at the time. 2026 JH2, similar in size, told a very different story. This time, telescopes caught it 8 days out. Scientists tracked it, confirmed its path, and proved conclusively it would miss Earth entirely. The outcome could not have been more different, not because the rock itself behaved differently, but because the detection system watching for it had improved. That contrast captures the entire point of planetary defense work happening quietly around the world every single day. Chelyabinsk represents the failure scenario, a warning arriving too late to matter. 2026 JH2, despite its own uncomfortably short notice, represents real progress, a system that caught something dangerous-sized, with enough time to calculate, confirm, and reassure an entire planet. Progress, though, is not the same as solved. 8 days of warning sounds reassuring only until you ask the next obvious question. What happens the day a rock this size gets discovered with far less warning than that? Continuing with chapters 18 through 33, maintaining the escalating intensity toward the final chapters on planetary defense. Rewind further into that Chelyabinsk morning, because the details matter more than the headline. It was a Friday, just after sunrise, an ordinary winter morning across the Russian countryside. Nobody expected anything unusual. Nobody had any reason to. The asteroid entered the atmosphere at an extremely shallow angle, closer to skimming than diving straight down, traveling at roughly 40,000 miles an hour, over twice the speed 2026 JH2 reached during its own close pass. That shallow angle mattered enormously. A steeper entry might have concentrated the blast in a smaller, more devastating area. Instead, the energy spread across a wider stretch of sky, a small mercy that likely prevented far worse damage on the ground. As the rock tore through the atmosphere, friction and pressure built up faster than the object could withstand. It shattered, then detonated, releasing its energy in one massive burst, roughly 14 miles above the ground. Dashcam footage, common across Russian vehicles at the time, captured the moment from hundreds of different angles, footage that would later let scientists reconstruct almost the entire event in remarkable detail. That footage became an unexpected scientific gift. By comparing the fireball's brightness, speed, and trajectory across dozens of independent camera angles, researchers calculated the object's size, mass, and total energy release with far more precision than typical asteroid events ever allow. Here is what they learned. The asteroid weighed roughly 10,000 tons, releasing energy equivalent to nearly 500 kilotons of explosive force. 90% of that mass vaporized instantly in the blast. The remaining fragments rained down as meteorites, one chunk large enough to punch a hole through the ice of a nearby frozen lake, later recovered by divers and put on public display. Chelyabinsk fundamentally reshaped how seriously the scientific community treats smaller asteroids. Before this event, most planetary defense attention focused on larger, kilometer-scale objects, rocks big enough to threaten entire regions or countries. Chelyabinsk proved conclusively that even a rock barely 20 meters wide, small enough to have gone completely undetected until the moment it exploded, could injure over 1,000 people and cause widespread destruction. Funding for detection programs increased substantially in the years following. More telescopes, more survey time, more computing power dedicated specifically to catching smaller, faster, more numerous objects. Exactly the size range that includes 2026 JH2. That connection is not accidental. When scientists raced to characterize this new asteroid within just 7 days, they were applying lessons learned directly from Chelyabinsk. Lessons about exactly how urgently objects this size deserve attention, and exactly how much damage an undetected version could cause. Chelyabinsk remains, over a decade later, the most thoroughly documented asteroid impact in human history. Every new rock discovered in this size range gets measured, quietly, against that morning in Russia, a reminder of what happens when detection fails and what stays possible when it succeeds instead. Here is an uncomfortable exercise worth walking through carefully. 2026 JH2 never threatened Earth. Scientists confirmed that clearly, well before closest approach. But understanding what could happen if timing had shifted reveals exactly why this size range earns such serious attention. Picture the same asteroid, same size, same speed, only its orbital timing shifted by a matter of hours rather than passing 56,000 miles away. In that altered scenario, Instead of sailing safely past, it would have entered Earth's atmosphere directly. Based on everything learned from Chelyabinsk, scientists can reasonably predict what that entry might have looked like. A rock in the 15 to 35 meter range, entering at typical asteroid speeds, would almost certainly explode in the atmosphere rather than reach the ground intact, just as the Chelyabinsk object did. Most asteroids this size lack the structural strength to survive atmospheric entry without breaking apart. The exact damage would depend heavily on where and how it entered. Over open ocean, which covers roughly 70% of Earth's surface, an explosion this size would likely go almost entirely unnoticed by anyone beyond scientific monitoring stations. Over a remote, unpopulated stretch of land, damage would remain limited to a relatively small radius, mostly affecting wildlife and vegetation. Over a populated area, the outcome could resemble Chelyabinsk, or potentially something more severe, depending on the precise altitude and angle of the explosion. Shattered windows, structural damage, injuries from flying debris spread across a radius, stretching multiple miles from the blast's center point. This is not meant to frighten you. It is meant to explain, honestly and directly, why scientists treat detection of objects this size as genuinely important work, rather than simple scientific curiosity. The difference between a fascinating flyby story and a genuine emergency often comes down to nothing more than a few hours of orbital timing shaped by gravity and physics long before any human ever discovers the rock involved. Here is the reassuring counterpoint. Objects in this size range, while capable of real regional damage, are not capable of the kind of global catastrophe associated with much larger asteroids, the kind that ended the age of dinosaurs roughly 66 million years ago. That level of destruction requires an object measured in kilometers, not meters, something 10,000 times more massive than anything discussed in this story. 2026 JH2 belongs firmly in the category of objects capable of serious, local, or regional harm, not planetary extinction. That distinction matters enormously for how seriously and how calmly this kind of story deserves to be treated. Serious enough to justify urgent tracking, not serious enough to justify panic. That balance, precise and carefully calculated, sits at the heart of every decision scientists made throughout this entire 7-day story. Space feels enormous, and it is, but the geometry separating a harmless flyby from a genuine atmospheric entry can come down to numbers far smaller than you might expect. Earth's atmosphere, the layer thin enough to actually interact with an incoming asteroid, extends outward roughly 62 miles from the surface. Compare that to the 56,000-mile distance 2026 JH2 maintained at its closest approach. This asteroid passed nearly 900 times farther away than the boundary of our atmosphere. That sounds like an enormous safety margin, and by most everyday standards, it is. But zoom out to the scale of this asteroid's entire orbit, stretching nearly 4 astronomical units across its full path toward Jupiter and back, and that 56,000-mile gap represents an almost impossibly precise threading of the needle, a near miss on a truly cosmic scale. Here is a comparison that captures the geometry involved. Imagine an enormous archery target, several miles wide, representing Earth and the space immediately surrounding it. An arrow fired from across an entire football stadium lands just outside the very edge of that target, missing by what feels like a comfortable margin up close, yet still representing extraordinary precision across that much distance. Small shifts, even shifts far smaller than the size of Earth itself, can separate a comfortable flyby from a direct atmospheric entry. A slightly different discovery date, a slightly different orbital calculation drawn from slightly different observation data. Any of these could have shifted the predicted path by enough to change the entire outcome. This is not meant to suggest 2026 JH2 came dangerously close to hitting Earth. It did not. The math confirmed zero impact probability well before closest approach, calculated with genuine confidence. This is meant to illustrate something different, how narrow the margins genuinely are across the broader population of near-Earth objects still waiting to be discovered. Scientists estimate that thousands of objects in this exact size range remain completely undiscovered, drifting on orbits nobody has calculated yet, simply because they have never happened to pass close enough or bright enough for existing telescopes to catch them. Somewhere among those undiscovered objects, geometry alone, the same geometry that kept 2026 JH2 safely at 56,000 miles, will eventually line up differently, not through any change in how dangerous these rocks are, simply through the ordinary unfolding of orbital mechanics across enough attempts, across enough undiscovered rocks, across enough time. That is not a prediction of doom. It is a statistical reality openly acknowledged by every scientist working in this field. And it is precisely why stories like this one, a close call handled well, matter so much. Each one sharpens the tools and the urgency, aimed at catching the next rock before geometry alone decides the outcome. As closest approach drew nearer, tracking 2026, JH2 stopped being an Arizona-only effort and became something closer to a relay race stretching across the entire planet. Here is why that global spread mattered so much. Earth rotates. Any single observatory can only see a given patch of sky during its own local nighttime hours, roughly half of any full day. To maintain continuous tracking of a fast-moving object, observatories, separated by enough longitude, need to hand off observation duties as darkness sweeps across different regions of the globe. Picture a baton passed continuously around a running track, except the track wraps around an entire planet, and each runner only holds the baton while their own patch of sky sits in darkness. As Arizona's sky brightened toward dawn, observatories in other time zones picked up tracking duties, keeping a continuous stream of fresh data flowing towards scientists working to refine the asteroid's exact path. European observatories contributed key observations during hours when American skies sat in daylight. The Virtual Telescope project, based in Italy and led by astronomer Gianluca Marsi, became one of the most active contributors during this stretch, capturing detailed images as the asteroid grew steadily brighter with each passing night. This kind of international cooperation happens remarkably smoothly, considering how many different countries, institutions, and funding sources are involved. Astronomers share data almost instantly through established networks, uploading new observations to shared databases the moment they are captured, available to researchers anywhere in the world within minutes. That speed matters enormously for an object with only a 7-day observation window. Every hour of delay, every hour spent waiting for data to reach the right hands, represented lost opportunity to refine calculations that grew more urgent by the day. Here is a detail that reveals just how collaborative this process really is. Individual astronomers, some working at major institutions, others operating smaller, amateur-grade equipment from backyard setups, all contributed observations that fed into the same shared tracking system. Professional and amateur astronomy blend together more than most people realize, especially during high-profile events like this one. By the final day before closest approach, telescopes spanning North America, Europe, and beyond had contributed enough combined data to narrow the asteroid's predicted path down to remarkable precision. No single observatory accomplished that alone. It took a coordinated, continuous relay stretching across 3 continents and multiple time zones, each contributor adding one more piece to a puzzle that needed solving fast. As the final hours ticked down, that global network shifted its focus one last time, away from calculating the orbit and towards something more immediate, capturing the asteroid's actual closest approach, LIV, for anyone watching around the world. Roughly 3 hours before reaching its closest point to Earth, 2026 JH2 passed by the Moon first, a quieter, less dramatic moment that nonetheless offered scientists one more valuable data point before the main event. Picture the asteroid's path as a single, continuous line arcing through space. The moon sat almost directly along that line, close enough that the rock swept past our closest neighbor hours before reaching Earth itself. This was not a coincidence born of careful planning. It was simply the geometry of this particular flyby, the moon happening to sit near the asteroid's path as it swept inward. This lunar passage offered scientists something valuable. One final chance to refine measurements against a perfectly known, perfectly stationary reference point. The moon's exact position and distance from Earth are known with extraordinary precision, unlike the asteroid itself, whose exact path still carried some uncertainty even this close to closest approach. By measuring the asteroid's position relative to the moon during this passage, astronomers gained one more sharp, reliable data point to feed into their final orbital calculations. Think of it as checking your watch against a clock you know is perfectly accurate. One last calibration before the moment that actually matters. Here is what made this particular window so valuable for observation. As the asteroid swept past the moon, its brightness had already climbed substantially compared to just days earlier, now visible through moderately sized telescopes rather than requiring the most sensitive professional equipment available. Astronomers with backyard setups, not just major observatories, began catching glimpses of the object for the first time. That growing brightness told its own story. 2 nights earlier, this same asteroid sat at a faint magnitude of over 21, essentially invisible without serious equipment. By the time it swept past the moon, that number had dropped dramatically, brightening with every passing hour as distance to Earth shrank. Brightness and distance move in opposite directions for objects like this. As the gap closes, sunlight reflecting off the surface reaches Earth more directly, more intensely, and the object appears to glow brighter and brighter, even though nothing about the rock itself has changed at all. 3 hours remained between this lunar passage and the moment scientists and skywatchers around the world had been anticipating for an entire week. The asteroid had already outrun the moon. Now, faster and brighter with every passing minute, it raced directly toward its closest possible pass by the one planet that had been watching it the entire time. In the final hours before closest approach, 2026 JH2 accelerated, and that detail alone surprises most people hearing this story for the first time. How does an object speed up without an engine, without any force pushing it forward? The answer is gravity, specifically Earth's own gravity, pulling the asteroid inward as the distance between the two objects shrank. This effect, known as gravitational acceleration, works exactly the same way regardless of an object's size. The closer something gets to a massive body like Earth, the stronger that gravitational pull becomes, and the faster the object accelerates in response. Earlier in its approach, while still millions of miles away, the asteroid drifted at speeds shaped almost entirely by its solar orbit, roughly consistent with its overall 3.75-year cycle around the Sunday. As Earth's gravity increasingly dominated the equation during those final hours, the asteroid's speed climbed sharply, eventually reaching its peak velocity right around the moment of closest approach itself. Picture a skateboarder cresting a hill, moving slowly at the top, then picking up speed rapidly as the slope steepens beneath them. Earth's gravity created exactly that kind of slope for this asteroid, a steep, invisible hill in space that sent it accelerating hard through its final approach. The angle of approach mattered just as much as the speed. Unlike a direct, head-on trajectory, 2026 JH2 swept past Earth at an angle, its path curving around our planet rather than aiming directly toward it. That curved path, shaped by the combined pull of Earth's gravity and the asteroid's own existing momentum, is precisely what created a close flyby instead of an atmospheric entry. This bending effect has an official name: gravitational deflection. Earth's gravity does not just pull objects straight toward itself. It bends their path, redirecting trajectory even for objects that never come close enough to actually collide. The stronger the gravitational pull and the closer the passing distance, the more dramatic that bending becomes. For this particular asteroid, that bending effect was significant enough that scientists watched closely for any measurable change in its future orbital path, a subtle shift caused entirely by swinging so close past a planet as massive as Earth. Even a small deflection during this flyby could meaningfully alter exactly where the asteroid travels during its next approach, years down the line. As the final minutes ticked down, telescopes across the night side of Earth locked onto the same rapidly brightening point of light, watching speed and angle both peak simultaneously. The physics of an entire elliptical orbit compressed into one brief, closely observed moment racing past our planet. Somewhere in the flood of data pouring in during those final observation days, astronomers picked up on another detail. This asteroid was spinning, and spinning fast. A full rotation completed roughly every 21 minutes, remarkably quick compared to how slowly many larger asteroids typically tumble through space. Here is how scientists actually detect something as small as rotation speed on an object too distant to see any real detail. As an irregularly shaped asteroid spins, different sides catch sunlight at different angles, causing its overall brightness to rise and fall in a repeating pattern. Track that brightness pattern closely enough, and the timing of each repeated cycle reveals exactly how fast the object completes one full rotation. Picture a disco ball spinning slowly in a dark room, flashing brighter each time a mirrored panel catches the light directly, then dimming as it rotates away. An irregular asteroid does something similar, just far more subtly, its brightness rising and falling as its uneven, lumpy shape tumbles through space. A 21-minute rotation period counts as genuinely fast for an object this size. Many asteroids rotate far more slowly, some taking many hours to complete a single spin. Faster rotation often points toward a smaller, more solid object, one less likely to be a loosely bound pile of rubble, held together mainly by weak gravity. This detail matters for a specific scientific reason. Very small asteroids that spin extremely fast sometimes cannot hold themselves together at all if they are structurally weak. There is a rough speed limit beyond which a loosely bound rubble pile asteroid would simply fling itself apart, the outward force of rapid spinning overcoming the weak gravity holding it together. 2026 JH2, spinning steadily at 21 minutes per rotation, without any sign of breaking apart, suggests this particular rock likely holds together as a single, more solid structure rather than a loose collection of smaller rubble. That distinction matters for scientists studying asteroid composition broadly, since solid asteroids and rubble pile asteroids behave very differently if humanity ever needs to deflect one. Rotation speed also affects how scientists interpret brightness measurements used to estimate size. A fast-spinning, irregularly shaped object can create brightness swings that complicate size calculations slightly, one more layer of complexity added to that earlier uncertainty around this asteroid's true dimensions. None of this rotation data emerged easily. It required careful, repeated brightness measurements across multiple nights, patient work squeezed into an already impossibly tight 7-day window. And yet scientists managed it anyway, extracting a genuinely detailed physical profile from an object that, just over a week earlier, had been nothing more than an unexplained smudge of light on a telescope screen in Arizona. As closest approach neared, one particular effort stood out from the rest of the global tracking network. The Virtual Telescope Project, based in central Italy and led by astronomer Gianluca Masi, prepared to do something most observatories never attempt. They planned to broadcast the entire event live, letting anyone with an internet connection anywhere on Earth watch this asteroid's closest approach unfold in real time. This decision mattered for reasons beyond pure spectacle. Professional tracking data, the kind feeding into orbital calculations at major laboratories, rarely reaches the general public in a format anyone outside the scientific community can actually understand or enjoy. A live broadcast changed that completely, transforming an abstract news story about distant orbital mechanics into something people could watch unfold with their own eyes. The technical challenge involved was substantial. Robotic telescopes, controlled remotely and programmed to track a specific, rapidly moving target, needed to lock onto an object, growing brighter and shifting position by the minute. Unlike photographing a distant, stationary galaxy, tracking a near-Earth asteroid during its closest approach requires constantly adjusting the telescope's aim, following a target that moves noticeably even during a single photo exposure. Early images captured by the project, taken while the asteroid still sat over 800,000 kilometers away, already showed a clear, trackable point of light against the star field behind it. As the days passed and the distance shrank, that point grew steadily brighter, each new image adding to a visual record of the asteroid's approach that anyone could follow online. Here is what made this broadcast genuinely valuable beyond simple entertainment. Watching a live stream lets viewers absorb information differently than reading a headline ever could. Seeing an actual point of light creep steadily across a star field, night after night, growing brighter as it approaches, builds an intuitive understanding of orbital motion that numbers alone rarely provide. The broadcast also served a quiet reassurance function. Uncertainty tends to breed anxiety, especially around any story involving the words asteroid and Earth in the same sentence. A live, transparent broadcast, hosted by an actual astronomer explaining what viewers were seeing in real time, offered a direct, honest alternative to rumor or exaggerated headlines. As the broadcast's start time approached, viewers around the world tuned in from wildly different time zones, some watching during their own evening hours, others catching the stream well past midnight local time, all drawn by the same rare opportunity, watching a genuinely record-close asteroid pass by their planet, live, as it actually happened. Somewhere in Italy, cameras locked onto the night sky, waiting for one small, fast-moving point of light to reach its brightest, closest moment yet. Numbers on a screen tell part of this story. Watching brightness climb in real time tells the rest, and that is exactly what viewers following the live stream experienced during the final hours before closest approach. 12 days before closest approach, at the very moment of discovery, 2026 JH2 glowed at a faint magnitude of 21.3, a number so dim it required serious professional equipment just to detect at all. Remember that magnitude works backward from what feels intuitive. Lower numbers mean brighter objects, higher numbers mean fainter ones. A magnitude over 21 sits deep in the range only powerful telescopes can reliably capture. By the day of closest approach, that same asteroid had brightened to roughly magnitude 12.8, an enormous jump representing a rock growing thousands of times brighter over the course of just over a week. That shift alone tells the entire story of this flyby in a single number, an object racing rapidly closer, reflecting more and more sunlight back toward Earth with each passing hour. Picture a candle carried slowly toward you across a dark room. From far away, it barely registers, a faint flicker easy to miss entirely. As the distance closes, that same small flame grows steadily more obvious, more impossible to ignore, without the candle itself changing in any way at all. At its absolute peak brightness, right around closest approach, this asteroid reached approximately magnitude 11.5, bright enough to spot through a moderately sized backyard telescope under genuinely dark skies, though still roughly 100 times too faint for human eyes alone to detect without equipment. That final detail matters enormously for how this story actually played out for most people on Earth. Despite passing closer than almost any recorded object its size, despite brightening dramatically over just a handful of days, this asteroid remained completely invisible to anyone looking up without a telescope in hand. No naked eye witnessed this event directly, anywhere on the planet. This created an interesting tension throughout the entire story. Professionally, scientifically, this flyby counted as a major, closely tracked event, rich with genuine data and rare observational opportunity. Practically, for the average person standing outside and looking up, absolutely nothing visible happened at all. That gap between scientific significance and visible spectacle explains why live streams like the one from Italy mattered so much. Without specialized equipment and expert guidance, this entire dramatic week would have unfolded completely invisibly, a record-close encounter passing directly overhead, while the vast majority of Earth's population remained none the wiser, eyes fixed on an ordinary, unremarkable night sky. Every countdown eventually reaches zero, and for 2026 H2, that moment arrived at approximately 6 p.m. Eastern Time, 21:23 Coordinated Universal Time, on Monday, May 18th. This was the precise second scientists around the world had spent 7 frantic days calculating toward. At that exact moment, the asteroid reached its closest point to Earth, roughly 56,000 miles away, moving at its peak velocity, brightened to its maximum visible magnitude, positioned exactly where a week of continuous international tracking had predicted it would be. Here is what scientists were actually watching for during that critical window, beyond simply confirming their calculations proved accurate. Every close approach offers a genuine opportunity to test and refine the tools used to predict future events exactly like this one. If the asteroid arrived precisely on schedule, at precisely the predicted distance, that success validates the entire chain of calculations, observations, and software behind the prediction. If reality diverged even slightly from prediction, that gap would matter just as much, revealing exactly where existing tracking methods need improvement before the next uncertain, fast-moving object appears with even less warning than this one received. Fortunately, this flyby unfolded almost exactly as predicted. The asteroid arrived within the calculated uncertainty window, confirming that even under an extremely tight 7-day timeline, the global tracking network had performed its job with genuine precision. Beyond validation, scientists used this narrow window to gather every additional scrap of data physically possible: brightness measurements, precise timing data, any subtle signs of the asteroid's shape or rotation, all captured during the brief minutes surrounding closest approach, when the object sat at its brightest and most observable point. This is the paradox sitting at the heart of every asteroid flyby story. The most scientifically valuable moment, the point of closest approach, is also the briefest. Within hours, the asteroid would already be pulling away again, distance increasing, brightness fading, the rare observation window slamming shut almost as quickly as it had opened. Picture a shooting star, but stretched across days instead of seconds, building slowly toward one brief, intensely watched peak, then fading away just as gradually afterward. That is the actual shape of an asteroid flyby, not a single dramatic instant, but a full arc, most of it invisible, all of it aimed toward one carefully predicted, carefully observed moment of closest approach. As that moment finally passed, scientists across 3 continents allowed themselves a brief, genuine sense of relief. The math had worked, the world had watched safely, and already attention was beginning to shift toward an entirely different question: what happens now? Here is a detail that surprised many people who first heard about this flyby. Despite passing closer to Earth than almost any recorded object its size, despite achieving genuine record-close status among tracked asteroids, nobody on Earth saw 2026 JH2 with their own eyes, anywhere, at any point during the entire event. Understanding why requires separating 2 things people often confuse: distance and visibility. An object can pass remarkably close while still remaining completely invisible, simply because visibility depends far more on size and reflectivity than on distance alone. Consider the numbers involved. At its brightest, this asteroid reached magnitude 11.5. Human eyes, under absolutely perfect dark sky conditions, can typically detect objects down to around magnitude 6, and that requires genuinely excellent viewing conditions, far from any city lights. The gap between magnitude 6 and magnitude 11.5 represents roughly 100 times difference in actual brightness. Not a small margin, but a massive one. Picture standing in a completely dark field, trying to spot a single lit candle positioned exactly 100 times farther away than a candle you could normally see clearly. That gap is roughly what separated this asteroid's actual brightness from the threshold of human visibility, even at its closest, brightest moment. Here is why that gap existed despite the extraordinarily close pass. This asteroid was simply too small. Even 56,000 miles away, an object only 15 to 35 meters wide reflects a genuinely tiny amount of sunlight back toward Earth, nowhere near enough to register against the human eye's limited sensitivity, even under perfect conditions. Compare this to the Moon, a genuinely massive object, over 2,000 miles wide, reflecting enormous amounts of sunlight, even from nearly 240,000 miles away. Size, far more than distance alone, determines whether something becomes visible to unaided human eyes. This distinction explains why telescopes mattered so critically throughout this entire story, not just for detection and tracking, but for the actual viewing experience during closest approach itself. Without specialized equipment, this record-close encounter remained entirely invisible, its drama unfolding purely within scientific instruments and calculations, never becoming a visible spectacle for the general public. That invisibility carries an important lesson buried inside it. Somewhere above your head, right now, in broad daylight or complete darkness, objects exactly this size could be passing by at exactly this kind of distance, and you would have absolutely no way of knowing, no way of seeing it, no visible warning whatsoever. The only real defense against that invisibility is exactly what made this entire story possible in the first place: telescopes, patient observation, and a global network of scientists dedicated to catching what human eyes never could. Once closest approach passed, 2026 JH2 did not simply disappear or dissolve into irrelevance. It continued along its long, stretched orbital path, gradually pulling farther and farther away from Earth, beginning the outward stretch of its journey back toward the distant reaches near Jupiter's orbit. Within days, the asteroid faded rapidly back toward invisibility, its brightness dropping just as dramatically as it had climbed during the approach, this time in reverse. Telescopes that had tracked it so closely during the flyby gradually lost the ability to detect it at all, the object shrinking back into the same faint, distant obscurity it had emerged from barely 2 weeks earlier. This fading was expected, unremarkable, and completely normal. Every asteroid flyby follows this same basic shape: approach, brighten, pass by, fade, disappear. What made this particular story worth telling was never really the aftermath. It was the unusually tight window, the record close distance, and the genuine uncertainty scientists worked through during those first frantic days of discovery. Here is what scientists actually gained from this brief, intense observation window before the asteroid faded away again. A refined orbit, calculated with far more precision than would have existed without this close pass. A better estimate, though still not a perfectly resolved one, of the asteroid's physical size. A confirmed rotation period. And critically, enough data to reliably predict when this same object will return. Based on its 3.75-year orbital period, scientists can already sketch a rough timeline for 2026 JH2's next several passes near Earth's neighborhood. Unlike this most recent encounter, discovered with barely a week of warning, future approaches will benefit enormously from everything learned during this flyby. The orbit is catalogued now. The object is permanently entered into tracking databases used by observatories worldwide. This transformation, from a complete unknown to a fully documented, permanently tracked object, represents the quiet, unglamorous victory hiding inside this entire story. 2026 JH2 will never again sneak up on scientists the way it did during those first uncertain days back in May. It has effectively been added to a growing catalogue of the solar system's known inhabitants. One more piece of the enormous, ongoing effort to map out everything sharing our own cosmic neighborhood. The rock itself, meanwhile, continues along completely unaware of any of this. It carries no instruments, no memory, no awareness of the global attention it briefly commanded. It simply follows the same physics-dictated path it has followed for millions of years, swinging outward toward Jupiter's distant orbit, before eventually curving back inward again, on schedule, roughly 3¾ years from now. For scientists, though, this quiet, unremarkable ending mattered enormously. A close call, handled well, understood thoroughly, and now permanently documented for whatever comes next. Step back from this single asteroid, and a much larger, more unsettling pattern comes into focus. 2026 JH2 was discovered only 8 days before its closest approach. That short window was not unusual. For objects this size, it is closer to normal than exceptional. Scientists estimate that only a small fraction of near-Earth objects in the 15 to 35 meter size range have actually been discovered and catalogued. The overwhelming majority remain completely unknown, drifting on orbits nobody has calculated, waiting to be spotted for the first time, likely under circumstances remarkably similar to this exact story. Here is why detection remains so difficult for objects this size. Smaller asteroids reflect far less sunlight than larger ones, staying below the detection threshold of most telescopes until they swing unusually close to Earth. And unusually close, as this entire story demonstrates, often means only days of advance warning, sometimes even less. Picture the night sky as an enormous, mostly empty field, and every undiscovered asteroid as a single dark stone scattered somewhere across that field, invisible until sunlight happens to catch it at exactly the right angle. Current telescope technology catches a meaningful percentage of the largest, most reflective stones. Smaller, darker ones routinely slip through unnoticed, sometimes for years, sometimes forever, until one happens to swing close enough to finally register. This gap in detection is not a secret hidden from scientists. It is openly acknowledged, actively discussed, and directly responsible for ongoing efforts to build better, more sensitive survey telescopes capable of catching smaller objects earlier, with more warning time than this particular flyby allowed. Here is a number worth sitting with. Some estimates suggest that thousands of objects, roughly this size, pass within lunar distance of Earth every single year. The vast majority never detected at all, either too faint to catch or simply never observed during their brief close approach window. That statistic does not describe a planet under constant, serious threat. It describes a planet with an incomplete picture of its own immediate neighborhood, one being filled in gradually, survey by survey, discovery by discovery, each new asteroid, like this one, adding another data point to an enormous, ongoing effort. 2026 JH2 represents a genuine success story within that larger effort. A small, previously unknown object, caught, tracked, and understood, all within a single week. But it also represents a pointed reminder of everything still slipping through, undetected, somewhere out there right now, following its own quiet path toward a discovery that has not happened yet. Here is a shift in thinking worth making before this story reaches its conclusion. When most people imagine asteroid danger, they picture size as the defining factor. Bigger equals scarier, smaller equals safer. Scientists who actually work in planetary defense think about this differently. Warning time matters just as much as size, sometimes more. Consider two hypothetical scenarios. In the first, a large, dangerous asteroid gets discovered decades before any possible close approach. Its orbit calculated and refined over years of careful observation. Plenty of time for scientists to plan, prepare, and, if truly necessary, even attempt deflection. In the second scenario, a much smaller asteroid, similar in size to 2026 JH2, gets discovered only days before arrival, leaving essentially no time for anything beyond basic tracking and prediction. Which scenario actually represents greater practical risk? Scientists generally agree that warning time, not raw size alone, determines how much genuine danger a given object poses in practice. A large asteroid discovered decades early offers humanity real options. A smaller asteroid discovered days early offers almost none, beyond simply watching and hoping the math holds. Fortunately, in the case explored throughout this story, the math did hold, cleanly and completely. But the tight timeline itself, 7 days between discovery and closest approach, represents exactly the kind of scenario planetary defense experts worry about most, not because the object itself proved dangerous, but because the response window proved so narrow. Picture the difference between spotting a storm forming on the horizon days in advance, giving you time to prepare, versus glancing outside and discovering it is already raining. Both might turn out to be nothing more than a passing shower. Only one gives you any meaningful chance to actually do something differently beforehand. This is precisely why survey telescopes, discovery networks, and rapid confirmation systems matter so enormously, arguably even more than deflection technology itself. Humanity has, in recent years, actually tested asteroid deflection techniques successfully. But deflection only works with sufficient advance warning, ideally years, not days. An object discovered 8 days before closest approach, like this one, offers essentially zero deflection window, regardless of available technology. If 2026 JH2 had posed genuine danger rather than a safe, record-close flyby, scientists would have had no realistic time to respond beyond issuing warnings and preparing for potential impact. That sobering reality reframes the entire value of this story. The genuine victory here was never about deflecting anything. It was about detection, confirmation, and calculation, executed successfully under serious time pressure, and it highlights clearly and directly exactly where the next major investment in planetary defense truly needs to go. Earlier detection, longer warning times, and fewer stories that begin with only 8 days on the clock. Behind every asteroid story like this one sits a quiet, ongoing, worldwide effort most people never think about. A genuine planetary defense network built specifically to catch objects like 2026 JH2 earlier, with more warning before they arrive as last-minute surprises. This network includes survey telescopes scattered across multiple continents, each one scanning different portions of the sky every single clear night, feeding observations into shared databases accessible to astronomers worldwide. Mount Lemmon, the observatory that first spotted this asteroid, represents just one piece of a much larger, coordinated system, working alongside similar survey programs across the United States, Europe, and beyond. Newer, more powerful telescopes continue joining this effort, each generation more sensitive than the last, capable of detecting fainter, smaller, more distant objects than ever before. Some of these newer instruments are specifically designed to survey enormous portions of the sky rapidly, dramatically improving the odds of catching small, dark asteroids earlier than current technology typically allows. Space-based detection represents another growing frontier. Telescopes positioned in space, free from the atmospheric interference and daylight restrictions that limit ground-based observatories, offer the potential for dramatically earlier detection, particularly for objects approaching from directions difficult to observe from Earth's surface, like the sun's own glare, exactly the blind spot that hid the Chelyabinsk asteroid until the moment it exploded. Here is why this entire effort matters so directly to the story of 2026 JH2. Every improvement to this detection network, every new telescope, every refined tracking algorithm, exists specifically to shrink that uncomfortable 8-day discovery window down further, ideally toward weeks, months, or even years of advance warning instead. This is not abstract, future-focused science fiction. It is active, ongoing, currently funded work happening right now across observatories worldwide, motivated directly by exactly the kind of scenario this entire story has walked through, step by step. Picture an enormous, invisible net slowly being woven across the sky, thread by thread, telescope by telescope, survey by survey, each new instrument tightening the mesh just slightly, catching objects that would have previously slipped straight through undetected. That net remains far from complete. Thousands of objects like this asteroid still slip through every year, undiscovered until they arrive close enough to finally register. But that net grows tighter every single year, driven directly by stories like this one. Close calls that unfold safely, thoroughly documented, and immediately absorbed into the next round of planning, funding, and technological improvement. 2026 JH2 will likely be remembered within the scientific community, not primarily as a dangerous object, because it never was one, but as one more valuable data point pushing that global detection network one step closer to catching the next unexpected visitor with more than just 8 days of warning. Every story eventually arrives at its final question, and this one deserves a direct answer. What did 2026 JH2 actually change? Now that the flyby has passed, the data has been collected, and the asteroid itself has faded back into the darkness it emerged from just weeks earlier. The most immediate answer involves precision. Scientists now possess a far more refined orbit for this specific object, precise enough to reliably predict its next several passes near Earth's neighborhood, years in advance, rather than scrambling with only days of notice, the way this most recent encounter unfolded. The second answer involves validation. An entire international tracking network, built and refined over years of preparation, proved itself capable of handling a genuinely tight, high-pressure timeline. Discovery, confirmation, classification, orbital refinement, and safe passage, all compressed into a single week, executed successfully across telescopes spanning 3 continents. The third answer, and perhaps the most important one, involves honest acknowledgement of exactly what still needs improvement. An 8-day warning window, however successfully managed, remains far shorter than anyone working in planetary defense actually wants. This flyby succeeded because the math worked out safely. Success should never be confused with comfort, and nobody within the scientific community treated it that way. Here is the broader truth this entire story ultimately reveals. Earth exists within a genuinely busy neighborhood, filled with thousands of small, mostly harmless objects, the overwhelming majority of which pose no real threat whatsoever. Occasionally, one of those objects happens to pass unusually close, offering scientists a rare, valuable window to study something up close that normally stays hidden in the vast emptiness between planets. 2026 JH2 represents exactly that kind of opportunity, handled about as well as an 8-day window realistically allows. Discovered quickly, confirmed rapidly, tracked precisely, understood as thoroughly as limited time permitted, and ultimately passed by safely 56,000 miles away, closer than nearly every recorded object its size, yet never once posing genuine danger to anyone below. That combination, genuine rarity paired with genuine safety, is exactly what makes stories like this one worth telling in the first place. Not fear, not danger. Rare, precise, quietly remarkable science, unfolding in real time, across telescopes spanning the entire globe, all focused on one small, fast-moving rock that nobody even knew existed 2 weeks earlier. Somewhere out there, right now, the next version of this story is already unfolding, unnoticed, on some unremarkable rock still drifting quietly through the darkness. Nobody has spotted it yet. Nobody knows its size, its speed, or exactly when it might swing close enough to matter. When it finally does appear, faint and unexplained on some telescope screen, somewhere on Earth, the entire process will begin again, exactly as it did this time. Racing against a clock nobody chose to start, but everybody now knows how to answer.